Gravity is weird. Keeps your feet on the ground. But it can also bend space, slow down time, and maybe, just maybe, be carried by invisible particles we've never detected. So what is gravity really? A force? A shape? Or something far stranger? In particle physics, every fundamental force has a carrier. Electromagnetism has the photon. The strong force has gluons. The weak force has W and Z bosons. And then, there's gravity. We've never detected a graviton. No proof it even exists. Which leads to an uncomfortable question. What if gravity isn't a fundamental force at all? According to Newton, any two objects with mass attract each other. This idea was clear, measurable, and even came with a neat equation. F equals gm1m2 by r squared. It explained everything from falling apples to planetary motion. And for centuries it worked flawlessly, until it didn't. Newton's theory couldn't explain some strange things. Why clocks ticked slower near massive objects? Why light bent near stars, even though light has no mass? None of this made sense under Newton's model. Clearly, something deeper was going on. Then came Einstein, and in 1915 he proposed something revolutionary. Gravity could be the result of curved spacetime geometry. According to general relativity, mass and energy distort the fabric of spacetime. And what we perceive as a gravitational force is actually just objects following natural paths, called geodesics through that curvature. So, at large distances, it still looks like Earth is pulling the moon. But if the moon were to move much closer, its path would simply follow the bend in spacetime, not because it's being pulled by a force in the traditional sense, but because that's the shape of the space it moves through. Imagine it like a tablecloth. When you place a watermelon on it, it bends this fabric. More the mass, more the curvature. This curvature has dramatic effects. Time runs slower near massive objects, a phenomenon called gravitational time dilation. And near a black hole, this becomes extreme. Time for a distant observer nearly freezes at the event horizon. Light even bends around massive objects, creating gravitational lensing which lets us see galaxies hidden behind others. Light travels along bent paths, forming arcs, rings, even multiple images of the same galaxy. This phenomenon has helped us find galaxies so distant, their light took billions of years to reach us. These aren't predictions anymore, they've been observed and confirmed. Here's where it gets weirder. Yes, from a distance, gravity looks like a force. Objects accelerate toward each other. Equations still work. But the closer we zoom in, especially at cosmic or quantum scales, that force seems to be just the geometry of space-time itself. Gravity still behaves like a force. We can measure it, balance it, and feel it. But at its core, it may be a manifestation of geometry, and may not be a force carried by particles like the others. So, is gravity a force carried by a particle? Or is it the shape of space-time itself? Here's the twist, we don't know. Despite all our models, gravity doesn't quite fit with quantum mechanics so far. We don't have a working quantum theory of gravity. And until we do, gravitons remain an improving ghost, and Einstein's fabric remains a mystery. And remember, gravity doesn't just hold things down. It shapes galaxies. It bends light. It makes time run slower. It's everywhere, yet almost nothing is known for sure. How can the most familiar force be the one we understand the least?